Hey everybody, it's Ripley back again. Today we're going to talk about related rates of change. Related rates of change are sort of the Cadillac of word problems as far as calculus is concerned. They're not very difficult, but there's a process that you sort of want to go through to figure out how to solve the problem. Okay, so here, here's what I'm gonna give you an example of a related rates of change problem, so you can sort of understand what's going on. Related rates of change, first and foremost, means that when, for example, if you were to throw a rock into a still pool, right? So you drop this rock into a still pool, and what do we know happens? Well, we get ripples that go out, right, in concentric circles. Now, if you think about it, if I know certain things, like if I know the rate at which these circles are expanding, or the rate at which the radius of each one of these circles is changing, then I can relate that, no pun intended, to the rate at which the area of that circle is changing at any given time. Now, the way related rates of change work is, think of it as, I guess that work R, think of it as a snapshot, a very specific moment in time. Okay? Now, the best way to exemplify this is to actually do a problem dealing with related rates of change. So I'm going to say a 10-foot ladder, whoops, ladder slides away from a wall, or excuse me, slides down a wall. Whoops, wow, what's going on this morning? At 3 feet a second per second. How fast is it sliding away? Is it sliding away from the wall? From the wall? From the wall. When the top of the ladder, when the top is 6 feet from the ground. The ground. Okay, so let's give ourselves a quick sketch. Just like anything else, make sure that you draw a picture. So you got yourself a wall. All right, here's my wall. Here's my wall, and then here's my ladder sliding down it. Excuse me. So here's my ladder. Now, what do I know about the ladder? Well, I know that the ladder is 10 feet. 10 feet long. And this guy's sliding down the wall at 3 feet per second. All right? Now, we also know that the point at which, let's do this, the point at which the photo is taken, as we said before, is when this is 6 feet from the ground, right? Now, we know that as this thing slides down, the bottom is sliding out. And that's the question that we're trying to answer. Now, we want to put this in mathematical terms, and then there's a couple of rules that we need to talk about. All right? So first things first, we know, what do we know? Let's go back to black. I know, what do I know? If this is y, all right, let's make the vertical y, let's make the horizontal x. If I know, this is my question, by the way, I know that dx over dt is the thing that I'm looking for. Okay? I want to know how fast, there's a question mark by the way, how fast is it sliding away from the wall? So that would be dx over dt if this were right here were x, right? I know that dy over dt, it's moving down at 3 feet per second, which means that y is shrinking. So dy over dt would be negative 3 feet per second, wouldn't it? That makes sense. True? All right, what else do I know? I know that y, when the photo is taken, that snapshot in time, because it's only at that snapshot in time that we can figure this out. Otherwise, all of our information is going to change. So we're saying that y is 6 feet, and then if you think about it, I made this kind of easy, didn't I? If the ladder is 10 feet long and y is 6, then what does x have to be? Well, with Pythagoreans, you could pretty easily and quickly calculate that x is 8. Now, there's one major rule. There's a huge rule in related rates of change, and it's really the only rule. The rule is this: don't plug in anything, don't plug, or pug, in any numbers until after the, whoa, man, I have not had my coffee. Whoa, 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 whoa. let's go. Don't plug any numbers into an equation, into the equation, if the quantity is changing, okay, let's put a little comma there, until after the derivative is taken. Deriv is taken. Now you may be going, Ripley, what are you talking about? Well, bear with me for a second. So first things first, we need to come up, you're like, what equation? How am I doing this? Like what equation am I dealing with? Why did that just zoom in? That was weird. Well, let's just look at this guy. First and foremost, I have a right triangle there. So I need an equation that I can take derivatives of, right? I mean, hopefully everybody agrees with that. I want to try and zoom this thing back. I don't know what I did there, but apparently we were zoomed in for the time being. When I see a right triangle, and I see x's and y's, and I see dx over dt and dy over dt, I start thinking Pythagorean's theorem. So let's just go, let's start with x squared plus y squared equals z squared. It's Pythagorean's theorem. And hey, at least it's a place to start, right? Excuse me. Now, I need a dx over dt, and I need a dy over dt. Or I need to manufacture one. So how do I do that? All I've got is an x, a y, and a z. And you're probably going, oh yeah, I've got that whole crazy thing called implicit differentiation. So, but let's look at this rule. This is my equation. Now, right now, if I plugged in a 6 squared plus 8 squared, I would indeed get 10 squared, but it helps me nary a bit to discover what dx over dt is. And that's my ultimate goal, right? I want to figure out how fast this thing is sliding away from the wall. Some of you may already be saying, wait a sec, isn't it sliding away from the wall at the same speed that it's sliding down the wall? Well, we'll figure that out here in just a sec. Okay, so what do I got? I've got an equation. I need a dx over dt, right? That's what I need. Well, that's pretty easy to manufacture, isn't it? What I can do is I can take implicit differentiation and manufacture that dx over dt and the dy over dt, because neither of those are t's. However, it says, the rule says don't plug in any numbers into the equation if the quantity is changing. Well, what's changing? We know that x is changing because we're sliding away from the wall. We know that y is changing because we're sliding down the wall, but is the latter changing? No. So I can actually put in that 10 squared if I want to. So I've got x squared plus y squared, both of which are changing, is equal to 100. And I'm going to use implicit differentiation to take the derivative, to manufacture that dx over dt. Well, the derivative of x squared is 2x. However, that's a t, that's an x. So I got a dx, well, hush my mouth, look at that, that's beautiful. Plus 2y dy over dt is equal to 0, because the derivative of a constant is 0. Now, what am I trying to solve for? Let's look close. This is my happy place. So I'm going to solve for that. So I know that dx over dt, let's put 2x dx over dt, is equal to negative 2y dy over dt. It should be obvious that my 2's canceled, right? So dx over dt is equal to negative y over x times dy over dt. Now, this is a really cool thing for two reasons. What I have is I just manufactured the thing that I needed. Look at it, it's sitting right here, just all pretty for me. Oh, all I have to do is plug in values. Now, not only do I have this neat little equation that I can use, I know what y is, I know what x is, and I know what dy over dt is. But if I needed other information, I could always go back to this original equation, the one that I started with. Notice how if I pay attention, good things happen, and I can manufacture those values. Like, for example, I didn't tell you that x was 8 feet away from the wall, right? You had to come up with that, and you use the original equation that we started with to do so. So let's go ahead and solve this thing. I got dx over dt is equal to, what, negative 6 over 8, actually known as 3/4, times negative 3. Which kind of makes sense, right? dx over dt is moving away from the wall. So it's not shrinking, it's growing. It has to be positive. So this guy is what, 18/8? Or what do we got, 9/4? And this is feet per second. Hey, they're not moving at the same rate. We also need to understand at this point that not only are they not moving at the same rate of speed, But this would change as this guy slides down the wall. You might ask yourself, Ripley, at what point would these guys be moving at the same rate? Well, you're probably like, well, that's pretty obvious. That's when this thing is 10 divided by root 2 above the horizontal, right? In other words, when you make an isosceles right triangle, now everything's moving, it's moving down the wall at the same rate that it's moving away from the wall. Okay, that's one example. I'm going to give you one more example, and then we're going to be done. And this one's not too bad. This is the world famous coffee filter problem. So here's the way the coffee filter problem works. Then we'll write it up. What I've got is, excuse me, let's say that I have a coffee filter that it's a big coffee filter, all right? This guy's going to be, whoa, no, I don't want that. This guy's going to be 10 inches across. Stop it. 10 inches across. And then let's say that it's, I don't know, let's make it 12 inches deep. Okay? And it's got water in it. And the water is filled up to, let's just make this 6 inches high. All right? All right, so what do we got? We've got water dripping out of the bottom of this thing. True? And this thing is, if the water's dripping down, this thing, excuse me, this thing is slow, this height of the water is slowly but surely decreasing, right? So this is the height of the water at time t. It just so happens that the height is 6 inches deep right now. So let's write up a problem. Let's make up a problem. I want to know at what rate is the volume of the water in the filter changing when the water is 6 inches deep. All right? Now, watch how this works, because this is pretty interesting. The cool thing about related rates of change is if you write down your information, all right? Oh, you know what? I am going to need a little bit, let's see. I want one more piece of information. So instead of 6 inches deep, I'm going to need one more little slice of information. And the water level is going down at 1/2 inch per minute. Okay? So let's write up what we have. Let's write up what we're looking for, and then let's see if we can answer this question. So first things first. At what rate is the volume of water in the filter changing? This is a quintessential related rates of change question. This is how the questions are typically framed. So how could I write that in mathese? At what rate is the volume of the water filter? At what rate is the volume of the water in the filter changing? Well, wouldn't that be dV over dt? That's what I'm looking for. Now, what else do I know? I know that I know that the height is 6 inches deep. And I also know that, let's see, what else do I know? Oh, I know dH over dt is 0.5 inches per minute. These are all of the things that I know. This is the thing that I'm looking for. Now, again, if you pay attention, notice this says dV over dt. If I've got if I'm looking for dV over dt, then don't I have to start with a v and then use implicit differentiation to take the derivative with respect to time? Well, what's the volume? Let's play. What's the volume of a cone? Well, volume of a cone, excuse me, is 1/3 the volume of the cylinder of the same base radius and height. So it's going to be pi thirds r squared times h. Now, if I take the derivative of this right now with respect, if I just do this guy, hopefully everybody sees that I'm going to get a dV over dt. However, the only piece of information that I have, or the only other pieces of information that I have is I have the height and I have the rate of change of the height. This r right here is going to give me fits. So hopefully, oh, there goes the bell. Ignore that, please. So hopefully you can see a way to get rid of this r so that everything is in terms of h's. Well, look at this. Let's see if we can come up with a way to use ratios, oh, similar figures, my favorite, right? So if this is the radius of the cone, when the snapshot is being taken, when the depth is 6 inches, and I know that the base radius of the cone is always 5 inches, can't I set up, I know that R is to H. Now, this is R is to H, this R and this H is in the water. This is the volume of the water, not the volume of the filter itself. The volume of the filter itself never changes. Excuse me, right? It's not changing. I know the radius of the filter. I know the height of the filter. Those things never change. So this is 5/12. So I know that R is equal to 5/12 H, which means I can rewrite my volume just a little bit. What's that? An ounce of prevention is worth a pound of cure. I can stay out of my own way, because otherwise when I take a derivative of this, I'm going to have a dr over dt and a dh over dt, and I'm going to have to take the derivative of a product, which makes things more complicated. However, now look at what I have. I have pi thirds. I know that R is always 5/12 H, so this is going to be times 25 1/44 H squared, right? That's just R squared. And this is going to be times H. So in a puff of, oh goodness, did I really just do this to myself? This is 25 pi, let's see, 300, 420, 432. So this is 432, that's right. Yep, that's right. 432 H cubed. So V, I'm going to rewrite this. V is equal to 25 pi 432 H cubed. Now I'm going to take the derivative with respect to time. Now you may say, Ripley, why aren't you plugging in 6 inches for the height? Ooh, 6 inches, did I? Oh, yeah, 0.5, got it. Well, what's the rule? What's changing in this little slice, this cone right here? The volume is changing, the height is changing, the radius is changing. Volume is changing, and all I care about is the volume and the height. They're both changing, so I can't plug any information in until after I've taken the derivative. So let's follow this guy up here. When I take the derivative of v with respect to t, I get 1 dv over dt. And then this guy turns into, 75 pi over 432 h squared dh over dt. Because I just differentiated h as though it was a t, so I leave a footnote. And look at that. It's perfect. It's sitting there. It's tailor-made for me. I know that dv over dt is equal to 75 pi over 432 times h squared times 0.5. Look at that. That's pretty awesome. And then I can just throw it in my calculator, and it tells me the rate of change of the volume at this very specific time. I got to plug these numbers in because I already took a derivative. This is after it's changing. If I plug them in before, look at what would happen. Had I plugged in 6 for h, I would have gotten a number here. And when I took the derivative of said constant, guess what it would have turned into? 0. So there are little warnings in there that you got to be really careful of. All right? Now, one thing that you are going to use, probably the vast majority of techniques that you're going to use, I would say 90% of everything that you do in related rates of change, is either going to have to do with similar figures, similar figures, like the one that I just used right here, or they're going to deal with right triangles, like the latter problem. Now, when you deal with a right triangle, and in some cases, you're going to deal with both at the same time. Kind of like over here. We had right triangles, but we had similar figures sort of trumped it. If I have right triangles, and this is x, and this is y, and this is z, and I've got x squared plus y squared plus z squared. Now, with related rates of change problems, what you never want to do is, plus z squared equals z squared. What you never want to do is solve for one of the variables first. Why bother? You're taking the derivative with respect to time. So I don't need to solve for any variables. I just roll through it. This is 2x dx over dt plus 2y dy over dt equals 2z dz over dt. You see what I'm saying? So it makes no sense to throw a square root in here, which just makes it more complicated. Nobody wants to deal with square roots when they take derivatives, right? Because they're a pain in the butt. So just leave it as x squared plus y squared equals z squared, and then roll through your problems. Okay? Now, you're going to do a lot of these, and you're going to do a lot of them with the assistance of your instructor, whether it's me or another instructor. All right? This is just an introduction to the thinking behind it, and that rule right there, that's your buddy. Okay? Before everything is said and done, you're gonna do quite a few of these. And they're a little bit tricky. You've never seen a word problem like them before. Don't panic. Relax. Don't forget to breathe. All right. I hope this was helpful. I hope you enjoyed it, and I look forward to seeing you in the next lesson.